The symbol I appears in both school physics and strength of materials, but it can describe two different quantities in rotational dynamics. Mass moment of inertia measures how mass is distributed around an axis. In beam theory, the second moment of area measures how cross-sectional area is distributed around an axis. Both use distance squared, but their physical meanings, units, and applications are different. Mass moment of inertia has units of kilogram meter squared and enters torque equals I alpha. Area moment of inertia has units of length to the fourth power and enters bending stress beam deflection and Euler buckling. This video builds the second idea from the first, so the familiar class 12 concept becomes a clear structural engineering tool rather than just another formula to memorize. Start with a rotating body. A small mass dm at perpendicular distance r from the rotation axis contributes r squared dm to mass moment of inertia. Adding every contribution gives I mass equals integral r squared dm. Two bodies with the same total mass can therefore have different rotational inertia. Move the mass farther from the axis and its influence grows with the square of distance. That is why a ring is harder to angularly accelerate than a solid disk of the same mass and radius. For the ring I equals mr squared. For the solid disk I equals 1/2 mr squared. Torque produces angular acceleration through torque equals I mass alpha and rotational kinetic energy is 1/2 I mass omega squared. This quantity belongs to motion and mass distribution. Now cut a prismatic beam and look only at its cross section. Instead of asking where the mass lies, beam theory asks where the area lies relative to a chosen reference axis. Replace dm by a tiny area dA and replace radial distance by the perpendicular distance y from the axis. The result is Ix equals integral y squared dA. This is called the second moment of area about the x-axis. Similarly, Iy equals integral x squared dA. It is a geometric property of the cross-section. Material density does not appear. The word second refers to distance raised to the second power, not to a second calculation. Because dA has units of length squared and y squared adds another length squared, area moment of inertia has units of length to the fourth power. A prismatic beam has the same cross-section along its length. Under ordinary linear elastic bending of a homogeneous beam, fibers on one side shorten, fibers on the other side lengthen, and one layer has zero longitudinal strain. Its intersection with the cross-section is the neutral axis. For this common case, the neutral axis passes through the centroid. The distance y in Ix equals integral y squared dA is measured perpendicular to that neutral axis. This condition matters. Moment of inertia is always about a specified axis. A section does not have one universal I. If the material is composite, if stiffness varies across the section, or if bending is unsymmetrical, the neutral axis may require a transformed section or stiffness weighted calculation. For the standard homogeneous prismatic beam, the centroidal neutral axis is our reference. Consider a rectangle of breadth b and total depth h. Take a thin horizontal strip at distance y from the centroidal x-axis. Its area is dA equals b dy. Its contribution is dix equals y squared b dy. Integrate from minus h over 2 to plus h over 2. This gives Ix equals b times the integral of y squared dy equal to by cubed over 3 between the limits. The final result is bh cubed over 12. Notice the cube on depth. If the depth doubles while breadth stays fixed, Ix becomes 8 times larger. About the vertical centroidal axis, exchange b and h, giving Iy equals hb cubed over 12. The same rectangle can therefore be very stiff about one axis and weak about the other. For a solid circle of diameter d, the centroidal second moment about any diameter is pi d to the fourth over 64. For a hollow circle, subtract the inner circle, pi times d outer to the fourth minus d inner to the fourth over 64. A rectangle gives BH cubed over 12 about its horizontal central axis. These fourth power and cubic effects explain why moving material outward is so efficient. An I section places large flange areas far from the neutral axis and keeps only enough web to carry shear and separate the flanges. Rotating a non-square rectangle by 90 degrees exchanges its strong and weak axes. Area stays unchanged, yet bending stiffness changes drastically. Always pair a numerical value of I with its axis and section orientation. Suppose we know the moment of inertia about a centroidal axis and need it about a parallel axis at distance d. Write each distance as y prime plus d, square it and integrate. The cross term contains integral y prime dA, which is 0 about the centroid. Therefore, I equals I centroid plus AD squared. This is the parallel axis theorem. The axes must be parallel and one of them must pass through the centroid. The theorem shifts an axis, it does not rotate one. For a thin plane area, the perpendicular axis theorem gives JO equals IX plus IY, where JO is the polar second moment about the perpendicular z-axis through the same point. The two theorems solve different geometric problems and should not be interchanged. Real beam sections are often assembled from rectangles, plates, channels or holes. First choose datum axes and calculate the centroid using area-weighted coordinates, then divide the section into simple parts. For each part, take its centroidal moment of inertia and add AD squared to shift it to the required neutral axis. Finally, sum every contribution. A hole is handled as negative area, so both its area and its moment contribution are subtracted. Units must remain consistent, usually millimeters to the fourth power. This method works because the integral over the complete area can be separated into integrals over individual regions. A common mistake is to add only the tabulated centroidal values and forget AD squared, even though the separation from the neutral axis is often the dominant contribution. Radius of gyration converts the distributed area into one meaningful distance. It is defined by k equals square root of I over a, so I equals ak squared. Some books use r instead of k. The idea is this: imagine replacing the actual area distribution by an equivalent concentration of the same total area distance k from the axis while keeping exactly the same second moment. For a symmetric picture, place half the area at plus k and half at minus k. Radius of gyration is not the average distance from the axis. Since I over a equals the area weighted average of y squared k is the root mean squared distance of the area, distant material influences k strongly. That is why two sections with equal area can have very different radii of gyration and very different structural performance. Watch the area distribution collapse into two equivalent strips. Every small element contributes y squared dA. Elements near the neutral axis contribute little. Elements far away contribute much more. Add all those contributions and divide by total area. The result is the mean value of y squared. Taking the square root gives k. If the entire area A were represented at the single square distance k squared, its moment would be ak squared, exactly equal to the original I. For a rectangle about its centroidal horizontal axis, I equals bh cubed over 12 and a equals bh, therefore kx equals h over square root 12. This distance is about 0.289 h. It does not mark a physical edge or material layer. It summarizes the complete distribution around the chosen axis. In simple bending, plane sections remain plane, so longitudinal strain varies linearly with distance y from the neutral axis. Hooke's law converts strain to stress. Equilibrium then gives the bending equation m over I equals sigma over y equals E over r. Therefore, sigma equals my over I. At the extreme fiber, sigma maximum equals mc over I, or m divided by section modulus z, where z equals I over c. For the same bending moment and material, a larger I reduces stress, but strength depends on I divided by the extreme distance c, not I alone. Moving area away from the neutral axis generally increases both I and section modulus, which explains the efficiency of I sections, box sections, and D beams. The sign of stress changes across the neutral axis, where bending stress is zero. Bending resistance combines material and geometry through flexural rigidity, EI. The curvature relation is M equals EI times curvature, and for small deflection it becomes EI times the second derivative of deflection approximately equal to bending moment. E describes how stiff the material is. I describes how effectively the cross-sectional area is arranged. Changing steel grade changes E only modestly, but changing section depth can change I dramatically. For a simply supported beam with a central point load, maximum deflection is PL cubed over 48 EI doubling. I halves the deflection, doubling span increases deflection by a factor of 8. This is why serviceability design often depends strongly on section geometry, even when the material stress is safely below yield. For a long column, Euler buckling load is pi squared EI minimum over effective length squared. Buckling occurs about the axis with the smallest second moment because that direction offers the least bending resistance. Substitute I equals AK squared and divide by area. Euler critical stress becomes pi squared E divided by L effective over K minimum all squared. The ratio lambda equals L effective divided by K minimum is the slenderness ratio. Radius of gyration therefore converts cross-sectional geometry into a length scale that can be compared with column length. A larger K minimum reduces slenderness and raises buckling strength. When checking a column, calculate both centroidal axes and use the smaller K. This is the practical reason radius of gyration appears so often in steel section tables. Area has several related moments. The first moment Q equals integral YdA and is used to locate centroids, and in the beam shear formula VQ over IT. The second moments Ix and Iy describe spread about in plane axis. The product of inertia Ixy equals integral xy dA helps with rotated axes and unsymmetrical bending. It is zero about axes of symmetry. The polar second moment Jo equals integral r squared dA equal to Ix plus Iy. For circular shafts, J enters the torsion equation T over J equals tau over radius. For non-circular sections, the torsion constant is generally not equal to the polar area moment, so blindly using J can be wrong. These quantities share similar integrals but answer different structural questions. Here is the complete workflow. Identify the loading and the bending or buckling axis. Locate the centroid, and for a homogeneous prismatic beam in simple bending, use the centroidal neutral axis. Compute I directly, use a standard formula, or assemble simple shapes with the parallel axis theorem. For bending strength, use section modulus I over C. For deflection, use flexural rigidity EI. For column stability, use the minimum radius of gyration square root of I minimum over A and the corresponding slenderness ratio. Remember the central idea: area near the neutral axis adds material but contributes little to I. Area far from the axis contributes through distance squared. Mass moment of inertia resists angular acceleration. Second moment of area does not contain mass. It measures geometric resistance to bending and buckling. Same mathematical pattern, different physical purpose.